Hi everyone. Today we're going to continue on with our discussion of chapter 28 by talking about several different Nobel Prize winning reactions for carbon-carbon bond formation in organic synthesis. And the first that we're going to talk about is the Suzuki reaction. For each of these reactions, we're going to talk about the catalyst that makes the reaction happen, and we're going to talk about the substrates of the catalyst. That means the starting materials that the catalyst takes and makes a new bond. And we'll talk about the substrate scope of each reaction, that is, how you can vary the starting material to get variations in the product. The Suzuki reaction is between an organic halide, an aryl or vinyl halide, and an aryl or vinyl borane. So let's talk about what we mean by that. I'll show you an example of a Suzuki reaction. Here's a benzene ring. This is an aryl halide. But in terms of substrate scope, vinyl halides work too. And then the other reactive partner is some kind of vinyl borane. These can be boronic acids or boronic esters, and we'll need to sort of make clear what we're talking about. So I'll show you an example of a vinyl borane or boronic ester. In general, we'll refer to these aryl or vinyl boronic esters or boronic acids as organoboranes. And we'll just refer to the halide as a vinyl or aryl halide. Let me finish the structure of this vinyl boronic ester. So I guess I'm all over the place here. This is a particular molecule that's called the benzene ring with the bromo is bromobenzene. It's an aryl bromide. But in general, aryl halides or vinyl halides work. What would be a vinyl halide? That would be something like this. And what would be an aryl halide? Something like this, where X is a halide. Generally, your text sticks with bromo. Other people have explored iodo and chloro, generally not fluoro. And then this reactive partner we're going to call, in general, an organoborane. In terms of substrate scope, the thing that's bonded to the boron can be either aryl or vinyl. And the other things on the boron can either be boronic acids, which would be something like this, where the thing bonded to the boron are OH groups, or it can be a boronic ester, where the thing bonded to the boron are OR groups. So what I've listed here, I guess, what I'm trying to do, and sorry for the confusion, is we're drawing a specific example of the Suzuki reaction, and then I'm trying to give you a sense for what the substrate scope of each of these reactive partners is. In other words, what else works. So with that in mind, let's show you what the catalyst is for this reaction, and then we'll show you what the product is. The catalyst is palladium 0. This is palladium with 4 triphenylphosphine ligands. That's a source of palladium 0 for reasons we talked about last time. And then you also need NaOH. And the purpose of NaOH will be illustrated in the reaction mechanism a little bit later. The product of this reaction is a new bond between the carbon that had the boron and the carbon that had the halide and the carbon that had the boron. In other words, we're going to make a new carbon-carbon bond between this aryl carbon and this vinyl carbon. So here's the product, and I'll illustrate that with, in red, the new bond that we made. And here is the orange aryl carbon, aryl carbon, and in blue, the vinyl carbon. Notice we've made a new carbon-carbon bond between aryl and vinyl. Notably, the stereochemistry of the vinyl borane is preserved. It is trans or E here, and it is trans or E there. It doesn't change. That stereochemistry stays the same. And that's an important feature of the Suzuki reaction. Before we discuss the mechanism of this reaction, let's look at a few variations so that we can get a sense for exactly how this works. Some of these are examples from your text to try to get a sense for the diversity and substrate scope. So here is an example practice problem from your text where we have this unusual vinyl borane. And this other somewhat unusual boronic acid. And we're going to, the Suzuki reaction is called a coupling reaction, kind of like the cuprate coupling reaction, because it involves making a carbon-carbon bond between the orange carbon, the vinyl carbon on this vinyl halide, and then this blue aryl carbon on the aryl boronic acid. So we would call this one an aryl boronic acid, and this one is a vinyl halide. So you can see in this example some of the substrate scope that we're getting. The halide doesn't have to be aryl, it can be vinyl. This is an example of a vinyl halide. And the organoborane doesn't have to be vinyl, it can be aryl. And so if we use these same conditions, the Suzuki reaction conditions, let's draw the product. I need a little bit more space, so I'm going to draw the boronic acid down here. Again, predicting the products of the Suzuki reaction is pretty easy because we just make a new bond between the orange and the blue carbons. And again, we need to remember that the stereochemistry in the starting material is preserved. So the new bond is going to be here. That's the new bond between the vinyl halide carbon and then the blue carbon from the boronic acid. And this is a step in the synthesis of the drug rofecoxib or Vioxx, which we talked about as a COX-2 inhibitor. Okay, so that gives you a sense for substrate scope. You should look at the other practice problems in the chapter 28 for exploring substrate scope in predict the products type questions. Before we discuss the mechanism of the Suzuki reaction, let's review methods we have just to prepare for synthesis questions. Let's review methods we have for making aryl or vinyl halides and methods we have for making organoboranes. So, aryl halides we can get from aromatic rings by electrophilic aromatic substitution using chemistry that we talked about in a previous chapter. So synthesis of aryl halides is pretty easy. Synthesis of vinyl halides can be a little bit more tricky, and you'll need to look at chapter 28 to review that a little bit, though. Let's say, for example, one of the ways that you can make a vinyl halide is by using some chemistry from 351. You could, for example, use HBr to do addition of one equivalent of HBr across one of the pi bonds in the alkyne, and that would give you this vinyl halide. Making other vinyl halides might be somewhat difficult, but that's, for example, one of the ways that you can do this. In most of the practice problems I'm looking at in your text, it looks like the aryl or vinyl halide is already prepared for you and you're good to go. All right. Let's instead now, let's talk about the synthesis of organoboranes. This is also going to involve chemistry that you learned in 351. Your method for doing this, well, there's actually a couple of methods, one of which is new and one of which is from 351. So the one that's from 351 is basically hydroboration of alkynes. So as an example of this, and this is a practice problem from your text, or rather this is an example from your text, you could take an alkyne, a terminal alkyne, and then you add this reagent, which is called catechol borane, and this will do regioselective and stereoselective hydroboration across one of the pi bonds of the alkyne. The hydride gets delivered to the more substituted carbon. The boron gets delivered to the less substituted carbon. It's a syn addition of BH across the carbon-carbon pi bond, and you end up with this vinyl organoborane. That's a pretty standard way, but it's limited in the sense that it's syn addition of boron and hydrogen across the pi bond of the alkyne, which always gives you the E vinyl borane. Your text doesn't really push you to make Z vinyl boranes, though it may have you use them as starting materials in various practice problems. If you want to make an aryl borane, that involves a slightly different set of conditions, some of which will involve reactions that you've seen before. So you need to start with a benzene ring, and you can do halogenation of the benzene ring via Br2 and FeBr3. You could do this with chloro as well. Then you add lithium metal to do halogen metal exchange. This is how we prepare organolithium reagents to begin with. We talked about this early on in 352. We didn't learn the mechanism for this reaction. It involves single electron transfer, and we're not really going to worry about that. But this changes the halide into an organolithium reagent. Then you react this organolithium reagent with this trimethoxyboron compound. It's called trimethyl borate. And we won't draw the mechanism of this reaction. Basically, the electrons from the carbon-lithium bond attack the boron to make an intermediate, a tetrahedral intermediate with a negative charge on the boron. And then one of the methoxy groups leaves, and that gives you the new carbon-boron bond with the two methyl groups there. The byproduct is the lithium counterion and the methoxy group. So these are two ways in synthesis you can prepare simpler molecules for the Suzuki reaction. Okay, let's do one more example of a Suzuki reaction, and then we'll talk mechanism. Here the halide is again going to be a vinyl halide. This is a vinyl iodide. And then the borane is going to be this particular organoborane that's prepared from catechol borane. And the conditions of the Suzuki reaction are palladium 0 chelated by 4 triphenylphosphine ligands, and with sodium hydroxide, that's going to make a bond between the iodide carbon and the borane carbon. Again, stereochemistry of the vinyl carbons is going to be preserved in the product. And this makes the following bond, which I'm going to illustrate in red, between the orange and the blue carbons. And again, stereochemistry of the two vinyl groups is preserved in the product. Notice that this is one way you can make a diene. And of course, dienes are substrates for Diels-Alder reactions. So you can imagine synthesis questions where you would need to make the diene first via a Suzuki reaction and then go on to do a Diels-Alder reaction. So we've talked Suzuki reaction predicting the products. We've talked stereoselectivity issues with stereochemistry of vinyl groups being preserved. We've talked about substrate scope. We've talked about how to synthesize the corresponding aryl halides, vinyl halides, and organoboranes using hydroboration of alkynes, or this new from 352 set of reactions, in particular this new step where the organolithium reagent reacts with the trimethyl borate to give you the aryl borane. And then we've seen another example of the Suzuki reaction. Let's now talk mechanism to understand exactly what's going on here. And For mechanism, let's just choose the simple example that we did to begin with the aryl bromide and the vinyl organoborane. All right. So often, if you look at what the catalyst is that we used, it's our starting catalyst, palladium tetrakis triphenylphosphine, or a palladium with four triphenylphosphines. The overall charge on the complex is 0, which tells you that the oxidation state, and you have 4, so 0 overall charge and 4 L-type ligands. So that tells you that the overall charge, the oxidation state of palladium is 0. Charge is 0, and each of the ligands when they leave is neutral. So overall charge on palladium has to be 0. That means palladium's in the 0 oxidation state. That means palladium is a D10 metal. There are 10 D electrons. Total electron count with those 10 D electrons plus the electrons from each of the ligands that are bonded to palladium, 2, 4, 6, 8, means we have 18 electrons total. That means palladium is coordinatively saturated. There is no place for an additional ligand to bind. So it should be no surprise that the first step is ligand dissociation. In order for the catalyst to be active, 2 triphenylphosphine ligands must dissociate. I'm not showing that mechanistically. It would presumably just look like this. Phosphine leaves with its electrons. That doesn't change the oxidation state of the metal. But it does change the number of ligands. So if you have 2 triphenylphosphine ligands dissociate, you're left with a palladium that now only has 2 phosphines on it, which we can represent like this. The overall complex is still neutral, so oxidation state is still palladium 0. There are still 10 D electrons present, but the total electron count is now 14. So there is space for additional ligands. And now this is the active catalyst, and now we're ready for the reaction. So I'm going to draw this reaction in sort of the same way that a lot of organometallic chemists will do. We'll have an arrow here. Trying to think about the best way to do this. Wonder if we need an entirely new page. And maybe we should just put this below. Okay. At this point, the catalyst is going to react with the aryl halide. So I'm going to draw that aryl halide here, and we'll have it coming into this reaction arrow, which is going to go like this. And this step is called oxidative addition. It's going to be like the oxidative addition step that we saw previously, when in cuprate coupling reactions. After the oxidative addition step, I'm going to have a bond between the halide and palladium, and I'm going to have a bond between the carbon and palladium. So this is my aryl carbon, and now that aryl carbon is bonded to palladium. On the other side, I still have my two phosphine ligands. So that's an oxidative addition step. If you wanted to push arrows, it would be like lone pairs on the bromo make a bond with carbon, and then the electrons in the carbon bromine bond make a bond with palladium. Or alternatively, you could say electrons in the bond between carbon and bromo end up in the bond between carbon and palladium, and the electrons from the two of the d electrons from palladium end up with a bond between palladium and bromo. In other words, you can't really tell if the situation is like this or like this. We can't tell. But either way is equivalent. And so I'm not going to worry about it. And in fact, people will generally not push arrows for this step. If you wanted to, the arrows might look something like this. We form a new bond with carbon at the same time as the carbon-bromine bond is breaking and attacking palladium. Again, people will generally not push arrows like that. If it helps you to do that, you can. You can tell that this is an oxidative addition because we have now two X-type ligands and two L-type ligands attached to palladium, but the overall complex is neutral. Therefore, the oxidation state of palladium must be palladium 2. We've gone from palladium 0 to palladium 2. In terms of d electrons, we've gone down by 2. There are only 8 d electrons. Palladium normally has 10 valence electrons. Its oxidation state is +2. Therefore, there must be only 8 d electrons. The total electron count of the metal is those 8 d electrons plus 2, 4, 6, 8 from the ligands. So a count of 16. Okay. The next step of the reaction, and maybe I will slide this over just a little bit. I need a little bit of space. Oops. Involves a step called transmetallation. And this involves the organoborane. So over here in the corner, I'm going to copy the organoborane structure. And OH minus is going to add to the boron. If you wanted to push arrows for that step, it's really easy. You just have to show negatively charged electrons on the oxygen, lone pair electrons on the negatively charged oxygen attacking boron to give you this anion. And I'm going to represent the catechol borane portion of this molecule with these two OR groups. This then becomes the substrate for a step that's called transmetallation. Which is essentially an exchange of the blue vinyl carbon on the boron for the pink bromo on the metal. They're going to switch places. And your text doesn't push arrows for that step, and neither will I, but it's essentially a substitution reaction. The more additional mechanistic details are probably available by people who know this area of chemistry better than me, but we won't talk about it, and you're not responsible for knowing the mechanistic details of this transmetallation reaction. In other words, you're not supposed to be able to push arrows for it. But you should see that the blue vinyl carbon has now been transferred to the palladium. The other two triphenylphosphine ligands are still there. And then what comes out the other side is Br minus and then the boron compound. Okay. So that's transmetallation. Again, mechanistically, what's going on is, I wanted that to be a better curve. Mechanistically, what's going on is you're replacing the X-type ligand Br on the palladium with the X-type ligand vinyl carbon still attached to the palladium. Stereochemistry is preserved. It was E before, it is still E afterwards. If we're counting oxidation state and d electrons, we've got two L-type ligands, two X-type ligands. We would conclude the same thing that we concluded above. So transmetallation doesn't change the oxidation state of the metal, doesn't change the d electron count, doesn't change the total count of doesn't change the total count of electrons. The next step is called reductive elimination, and that's going to take us back trying to figure out where to put this. Let's just put it here. The next step is reductive elimination, and this is going to be where, sorry, I'm just not liking aesthetically how this looks, but I guess we can all live with that. In reductive elimination, this is the coupling step. We're going to take the electrons from the carbon-palladium bond and the electrons between the aryl group and then the electrons from the carbon-palladium bond with the vinyl group. And we're going to make a new carbon-carbon bond between aryl orange carbon and blue vinyl carbon with one of those two pairs of electrons highlighted in blue and red respectively, and then the other pair is going to go back onto palladium. If you insisted on pushing arrows, you could do so like this, but it would also be just as fine to push arrows like this. You can't really tell which way it is, and in fact, I won't push arrows at all. And this is where I guess I need to draw my curved reaction arrow a little bit better so we have room. This is the reductive elimination step, and this is where we make the new carbon-carbon bond between aryl and vinyl carbons respectively. You can tell that this is a reductive elimination step because after it occurs, we're back to palladium 0 with a total d electron count of 10, a d electron count of 10, and a total electron count of 14. And so at this point, we're ready to continue onward. And this process occurs through these three alternating steps: oxidative addition, transmetallation, and reductive elimination, again and again and again and again. So this now allows you, the reaction's highly versatile. You should practice it a lot in synthesis. At the beginning of this chapter, I talked about how there are some bonds we didn't yet know how to make, and I talked about this bond and this one. And if you see a bond between two aryl carbons, you need to be thinking, I could have made that via the Suzuki reaction. And you can think your way backwards to some potential candidates. For example, we could choose to have one side be the halide and the other side be the organoborane. Which I'll abbreviate that way. Or you could potentially choose to have this side be the organoborane and this side be the halide. And at this point, there wouldn't be necessarily any particular reason why you should choose one versus the other. If you were going to make a distinction, maybe it would have to do with whether it's easier to synthesize the borane or the halide on either side. Okay, so that's the Suzuki reaction, widely used, and you should think about its use and how to in terms of predicting the products and providing the reagents. It's also totally fair for me to ask questions about mechanisms. Is this an oxidative addition step? Is this a reductive elimination step? Is this a transmetallation step? It's also a totally fair game for me to take any of these organometallic complexes and say, hey, what's the d electron count? What's the oxidation state? And so on. Okay, that's about all we have time for the Suzuki reaction. Now let's talk about the Heck reaction. Again, we'll overview the Heck reaction in terms of what the starting materials are and what the substrate scope is. And we'll do some predict the products type questions. And then we'll talk about what the mechanism looks like. It's going to also involve a lot of these similar, it's going to at least involve the oxidative addition and reductive elimination steps, though it's going to involve some other mechanistic steps that are similar, that are interesting and found in a lot of other organometallic type reactions. So, as before, I'll give you a specific example of the Heck reaction, and then we'll talk substrate scope. Like the Suzuki reaction, the Heck reaction involves some kind of sp2 hybridized carbon halide bond. So the halide can either be aryl or vinyl. Either of those is okay. And then the other partner is an olefin, but it's usually an olefin with an electron withdrawing group on it. So I'll give you one example. but the general substrate scope is that of a olefin with this general structure where Z equals a phenyl group, a benzene ring, an ester, or perhaps CN. Generally electron withdrawing group. And the product of the reaction is a coupling reaction between the less substituted carbon on the olefin and the aryl or vinyl carbon of the aryl halide. Like the Suzuki reaction, this is a coupling reaction between two sp3 hybridized carbons. Here is the new bond that is made. And interestingly, you get selectivity for a transalkene when such is possible. Why do I say selectivity? Before in the Suzuki reaction, I said the stereochemistry of the vinyl portion is preserved, and that's true. But of course, here in the Suzuki reaction, the vinyl organoborane has both portions, bromide and borane, have things on the sp3 carbons. Interestingly, in the Heck reaction, the carbon we're making the bond with is unsubstituted or has no particular halide or borane functionality. In other words, we're dealing with just CH bonds here. And so this process is going to be interesting, but there wasn't any stereochemistry about the olefin to begin with. But after we make the new bond in the Heck reaction, there is stereochemistry and it's selective for trans. On the other side, it's not clear from this example, but I'll show you a different example. On the other side, if the halide is vinyl, the stereochemistry of the halide is preserved. As an example, here's, and I haven't even shown you the catalyst for the Heck reaction, so stay tuned, but I do want to show you the substrates. Here's the vinyl halide, and here's the olefin. And the E stereochemistry of the vinyl halide is going to be preserved in the product. That one is still E. And then new stereochemistry in the olefin portion is also going to be selective for trans. So E selectivity in the vinyl halide is preserved, and E selectivity or trans selectivity in the olefin is now selected for by the conditions, by the reaction. The reaction favors E stereochemistry in the portion of the molecule that was the olefin. And again, this is a coupling reaction between the halide and the less substituted carbon of the olefin. Now, what about reaction conditions? It turns out that you also need palladium, though the Heck reaction starts with a different source of palladium. Palladium acetate, as you saw in the last lecture, is an example of palladium 2. There is the need for a ligand, and there are all kinds of different phosphine ligands that you might choose. The one chosen in the text is not triphenylphosphine. It's a little bit more sterically hindered. It's abbreviated as follows in your text. I will draw for you what that means. Maybe the best place to do that is here. Triorthotoluylphosphine involves a phosphine bonded to 3 benzene rings, where each of those benzene rings also has an ortho metal group. If you can think of a better way to abbreviate that, I'm interested. This is actually a more sterically hindered ligand than just plain old triphenylphosphine. As to why this is used in the Heck reaction instead of just triphenylphosphine, the answer to that is maybe murky and is embedded in history. When people invent reactions that need ligands like phosphines, they will often try a lot of things and they will choose to use the one that works best. It's possible that this is the one that worked best in context, but you may see, if you were going to get into this and read a lot of the chemical literature, a lot of different phosphine ligands used for the Heck reaction. The identity of the ligand can influence the rate and selectivity of the reaction. We're not going to worry about that, but I'm just going to stick with what's shown in the text. And finally, for the Heck reaction, you need a base, and that's triethylamine, which is a good non-nucleophilic base. Okay, so let's do a few, and those are the so-called Heck conditions, which I will copy and put here. I want to do a few additional predict products questions involving the Heck reaction before we talk mechanism. So these are examples straight out of your text. Here is an aryl halide. And here is an alkene. And then here are the standard Heck reaction conditions. Here is the new bond between, and in this case for the olefin, doesn't matter which of the 2 carbons, they're both bonded, but for the aryl halide, the 2 carbons rather in the olefin are identical to each other. In the aryl halide, it's the halide carbon, the aryl carbon bonded to the halide, that's going to get the new bond. So this would be the product of the Heck reaction. And then maybe just one more, also a practice problem from your text. Here is a vinyl iodide. That's your halide portion of the molecule. And then over here is your olefin. And that olefin is bound to a benzene ring with a methoxy group on it. Again, where your olefin is substituted, you're going to preferentially make the bond with the less substituted carbon. Again, we'll use the standard Heck conditions. Let me just clean those up a little bit to make it a little bit neater. The new bond is going to be between the vinyl carbon of the halide. This is the orange carbon. Notice that the stereochemistry there is E, and that stereochemistry is going to be preserved. Then notice we make a bond with the blue olefin carbon, and that establishes selectively E stereochemistry about that olefin, while leaving the rest of the molecule unchanged. Okay, that's a good stopping point. So let's pause, and when we come back, we'll discuss the mechanism of the Heck reaction, and then we'll have 2 additional reactions that we need to talk about.